Good afternoon. Welcome to
FamilyMath number 141a.
FamilyMath number 141a. So today we're going to talk about an amazing theorem called the Baaaaack-Karski theorem that you learned about by reading a book.
Yeah.
And we're going to end at the Hilbert curve, probably 5 videos from now. And in between we're going to take a detour
Of infinity.
through infinity. Okay?
Alright. Yeah.
Alright, so the Baaaaack-Karski theorems we're going to illustrate with oranges.
Yeah.
Okay? So the Baaaaack-Karski theorem is an amazing theorem that says you can take a sphere and you can cut it into 5 pieces, and one of those pieces actually is a single point.
Yeah.
So it's really like 4 pieces
And
plus one leftover point.
Yeah.
And you can reassemble those pieces to form
2 oranges.
2 spheres
The same
that are
size.
exactly the same size.
Wow.
Yeah, doesn't really fit with your intuition, does it?
No, that would be just twice the mass. The mass just doubles.
Seems like it, right?
Yeah.
Weird, right?
Yeah.
But you had a cool observation actually about one thing this implied. Remember what you said it meant?
Well, you could create infinity with this.
Right, you could just keep doing it every time, right? You could just, at step 1 I've got 1 orange, at step 2 I have
2.
at step 3 how many oranges would I have?
4.
4.
2 oranges, and then you keep going up the powers of 2, and eventually you get to infinity.
Yeah, so 1 orange could suddenly turn into infinitely many oranges. The other Baaaaack-Karski theorem, the second theorem, says you can take a ball of any size, slice it up, and turn it into, and put them back together into just a single ball of any size, including like as big as the Earth,
Well,
which is also completely not intuitive, right?
yeah.
So anyway, things involving infinitely many points get really weird.
Yes.
So one thing I just want to show you before we jump into talking about Hilbert curves is that the number of integers 1, 2, 3, call it positive integers, equals the number of even integers 2, 4, 6, 8, 10, etc.
But even numbers are only half.
Yeah, it's weird. It seems like I throw out this 1, I throw out this 3, I throw out that 5, I'm left with 2, 4, 6. Seems like I only have half of them, right?
Yeah. That they're the same.
But there's infinity of these, and there's infinity over 2 of these.
It seems like that would be the right way to think about it, right?
Except infinity over 2 is still infinity.
Well, it definitely is confusing.
Yeah.
And the way you figure out if 2 sets of objects are the same size is if you can match them up in what we call one-to-one correspondence. So one object from here goes to one object from here.
Yeah.
One object here goes to one object here.
Well, you can multiply each by 2.
And you hit, every one of these comes from one of those, and every one of these gets covered. You're absolutely right. You can just multiply by 2 times 2. 1 goes to 2, 2 goes to 4, 3 goes to 6, 4 goes to 8. Does every number here end up on a number here?
Yeah.
Yeah.
Does every number here get hit by a number from there?
Yeah.
Yeah.
Huh, so they must be the same size.
Wow.
The other way we could do it is the reverse. We could divide by 2 or factor a 2 out of this. It would be 2 times 1, 2, 3, 4, 5.
All the way up.
Hey, wait a minute. That's pretty weird, right?
Yeah.
You definitely didn't expect that, did you?
No.
No. Okay, well I'm going to show you how this can happen in geometry too.
Ooh, cool.
Okay? You ready to talk about that?
Yeah.
Alright, here we go.